Okay, so today we're going to be looking at different graphical models, and this is going to continue into the next few days. So we want to look at trends in graphs and rate of change. We're going to do that through looking at graphs that represent linear functions, quadratic functions, exponentials, all the types of functions that you've learned about so far. So, graphical models. A graphical model is a visual representation between two quantities. It shows how one quantity changes with respect to the other. Okay, so like I said, there's different types of graphs we can look at. Linear is representing on a graph with a straight line. Okay, so that's the first graph here. We can have it going upwards or downwards. And the slope is rise over run. The next type is quadratic, and that's making a parabola. So that can be a parabola that's facing down like the one shown, or you can have a parabola that faces up as well. Okay. So the different points on the graph here, there's the vertex, and this is the highest or lowest point of the parabola. There are x-intercepts, and it also shows the y-intercept there. Okay. Another type of graph is exponential. We have done a unit on this already. So we, just as a reminder, we have our exponential growth and our exponential decay, and that's what the exponential functions look like. Okay. So we want to describe the relationship in each graph. So this first one, we notice that we have a straight line, and that means this is linear. Okay. And as you want to look at the independent variable first and what that's doing, and then what happens with the dependent variable based on that. So as our hours worked increase, the earnings also increase. Okay. Here, going up by the same amount the entire time, that's what creates that straight line. So there's a constant increase. The next one, we're talking about compound interest, and we see we have time along the bottom and the amount of money along the side there. So looking at this one, we see this type of graph. The difference between exponential is that it starts low, goes high, or starts high and then goes low, where a quadratic, a parabola, is going to loop all the way around. So looking at this one is an exponential. And this is exponential growth, more specifically. So as time increases, the amount also increases. Okay, next one's here. We have temperature of a cooling cup of coffee. We have time along the bottom, temperature along the side. What we notice here is it's starting high and ending low, and there's a curve. Because of that curve, and because it's not looping back up, we have exponential here, and this is exponential decay. So as time increases, the temperature decreases. Okay. And fertilizing a field. So we have our fertilizer used along the bottom and our crop yield along the side. what we notice is there is a start and increase, and then once it hits a certain point, then there's a decrease. Okay, so because it has an increase and a decrease there, this one is quadratic. So it's increasing until we get to the vertex, and then it decreases. Okay, so certain words that we've used for trends. So we've talked about increasing, decreasing, and having a constant growth. So trends or patterns of change in a graph are often used to justify decisions and make predictions. Trends can occur in three broad groups: increasing, decreasing, and constant, or there is no change. Sometimes only short-term predictions are reliable, as we cannot be certain that a trend will continue. There are several factors that may affect a trend. Okay, so looking at the graph here, we have the aging of Canada's population. So we have three different lines or three different age groups here. So the red one is representing age 15 and under. The blue or purple line there is age 60 and over. And the green line is 80 and over. So use the graph to predict the number of Canadians in each age group in 2010. Okay, so what we notice here along the bottom is our years. Our graph is only going to 2000. So we would need to continue the graph on and predict what it would be in 2010. Okay, so we want to look at the trajectory of each line. And because this is outside of our data, we can remember that we're going to be using extrapolation in order to get these answers. Okay, so with our 15 and under group, we notice that this line stays pretty level as we go from 1990 to 2000. So we can say that it's going to remain around that 6 million mark. Looking at the 60 and over, we notice that there is a steady increase with this one. So we're going to assume that it's going to continue to increase, and it will also end up around 6 million in 2010. And if we look at the 80 and over, we can notice that there is a very slight increase as time goes on. So if it continued on, it's already reaching about 1 million, so we might get to about 1.5. Okay. What decisions might the Canadian government make in response to the trends in the graph? Okay, so we want to think about how many people there are in each age group and how that's going to affect the world. So if we're thinking about the group that is 15 and under, those are children that are not working, they are still living at home. The age group that's 60 and over, 60, you might be reaching the age of retirement. And then 80, that's you're in retirement. And so thinking about that, how you're getting the money when you retire. Okay, so we need to think about the Canada Pension Plan. And so the government would want to know how much money is being used, being paid out through pensions. So we would want to know how much funding there needs to be. Okay, that's one reason that they would be looking at this trend. Okay, so we're going to be talking about rate of change. So rate of change, this can be done using a table or a graph. The rate of change is rise over run, or it's y2 minus y1 over x2 minus x1. Okay, so doing a couple examples here. So our rate of change, y2 minus y1 over x2 minus x1. So the x's are the time, the y's are the height. So we would have the second one as our y2, the first one as our y1, over here again, x2, x1. Putting that in the formula, we have 1400, subtract 2000, and that's over 4 minus 0. What we get here is negative 600 over 4, and that gives us negative 150. And our units here are meters per minute. Okay, so that's the rate of change using a table. Now, rate of change using a graph. This one here, we have vehicle rental costs, we have the distance driven, and the cost of the rental. So we have 2 points on the graph. The one at the bottom here, we are calling x1, y1, and the one at the top, we're calling x2, y2. So back into the formula again, rate of change, y2 minus y1 over x2 minus x1, 700 minus 400 over 400, subtract 200. So we get 300 over 200, which is equal to 1.5, and our units are dollars per kilometer. Okay. Like we said, that our rate of change can also be our rise over run. So looking at this here, we would want to go how much we go up by, that's the rise, and how much we went over by, being the run. So using the graph here, it would be going up 1 to 300, which is where we get this number here, the rise, and going over 1 200, which is where we get the run of 200 here. Okay, so whether you're using the formula or rise over run and looking at a graph, you will get the same answer. Determine the slope of each line. So slope is also rise over run, or y2 minus y1 over x2 minus x1. So you can pick specific points on the graph you want to use. Okay, anywhere that lines up is a valid point. So I'm going to choose here and here. No matter what points you pick, you should end up with the same slope as what I'm calculating. So if you wanted to pick different points and try it on your own, as long as you end up with the same slope or rate of change, then you know you're on the right track. So picking these points here, the first point is 160, and the second point I chose is 120. So our slope we call m, y2 minus y1 over x2 minus x1. Okay, so the bottom point is my x1, y1. The top point is my x2, y2. So y2 is 120, subtract y1, which is 60, over x2, which is 2, subtract 1. So 120 minus 60 is 60, and 2 minus 1 is 1. So we get a slope of 60, and looking at our units, this is kilometers per hour. Okay, the next one talks about the depreciation of the value of a computer. So with this one here, we can pick a couple points and use our formula. Okay, I like to pick points where it lines up with the grid lines, otherwise you're kind of doing more estimating. So we can be a lot more accurate if we're on the grid lines. So that first point is 0, 1000, and the second point is 2.5 and 500. Okay, so again, y2 minus y1 over x2 minus x1. The x1, y1 is for that top point, the 0, 1000, and the x2, y2 is for the lower point, 2.5 and 500. So we have 500 minus 1000 over 2.5 minus 0. So this is a negative 500 over 2.5, and we get a negative 200. We notice our units here is dollars per year. Okay, the other thing I'd like you to notice here, the first one is this line is going in the positive direction, so we have a slope that is positive. The second one, we have a line going in the negative direction, so our slope is negative. Okay, so that's a good way to double check that you have the right answer. Okay, so the table shows the change in height of a tomato plant from germination until the tomatoes ripen. Okay, so we have time in weeks and our height in centimeters. So determine when the rate of change in the height is 0, constant, and changing. Okay, so we're going to notice here that our time in weeks is going up 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, going up by 2 each time. Okay. So that is good. Having your x going up by the same amount each time, we just need to focus on the change in our y, which is our height. So the change here, 5 minus 0 is 5. The next one, 10 minus 5 is 5. Next we have 20 minus 10 is 10. 40 minus 20, 20. 58 minus 40, 18. 75 minus 58, 17. 86 minus 75, 11. 90 minus 86 is 4, and 90 minus 90 is 0. Okay, so these are all of our rates of change that we have. So the first one is asking when the rate of change is 0. So we notice that we have a 0 right here, and that's going from 16 to 18 weeks. The next one is asking when it's constant. So that's when we have that same difference more than once. And we notice that we have a repeat, and that's between 0 and 4 weeks. We have that 5 twice, nothing else repeats itself. So from 0 to 4 weeks. And then it asks when our rate is changing. So it's remaining constant until week 4, and then all of it changes after that. Those are constant changes. So it's changing after week 4. B, when is the rate of change in height the greatest? So we're looking for the greatest difference here. Our biggest number is the difference of 20, and that's between 6 and 8 weeks. And lastly, we are being asked to describe the growth of the plant. So we can look, if it's just based on our rate of change here, we notice that it starts with a slow growth, and then it increases, and then it starts to decrease again. Okay, so the graph is showing a slow growth, and then it starts to go up quicker, and then that growth slows down again until it stops growing. So starting with the slow growth, then quick growth, and then it slows back down until it stops growing. Okay. So focusing on those different rates of change and what those mean. So when there is no rate of change, we notice that's from 16 to 18, and we notice that we have a straight line that goes across here. So when there's no rate of change, there's no growth, then that's a straight across horizontal line. When we have a constant change, so both of those 5s are there, we notice that from 0 to 4 weeks, that's actually a straight line in that region. And when we have changing growth, then our slope is different for each section as we go. So identifying rates of change in a table or graph. So as we just mentioned, when it's 0, then we are having that graph being a horizontal line. And the first differences are 0 if the rate of change is 0. When we have a constant rate of change, that's when we create a straight line. We'll have a linear part to our graph. And the first differences are equal. So the previous example is when we had 2 5s in a row, that was constant. And changing, this is when it's looking more of an exponential function. And the first differences are changing each time. So for most of the table on the previous slide, we had different numbers as our rates of change as we go up. And that's why we had all different pieces and different slopes as we were going through the graph. Okay. Something to keep in mind when it's constant, it can also be going down. It's not just the positive, also the negative direction. Okay, constant rate of change just means linear, no matter what direction it's headed. Okay, so you're going to be doing these textbook questions based around trends and graphs and looking at rates of change. If you have any questions, please let me know.